The Webb glance is such a long way out that it's catching light that has been voyaging for over 13 billion years. Yet, the universe has been expanding, and thus, the light has been stretching. For the most distant worlds, we're looking back in time nearly to the Big Bang. The immensity of the universe might seem vast, but every last bit of it started from what we refer to as the singularity. As of now, this is how we interpret the Big Bang hypothesis. Anyway, the James Webb Space Telescope, JWST, has revealed significant mysteries concerning the formation and growth of the universe, leaving us dumbfounded. Prestigious physicist Brian Cox has proclaimed that the noteworthy discoveries made by the JWST might actually reshape our understanding of the universe as a whole. Join us as we dive into these new heavenly discoveries that promise to change our comprehension. The James Webb Space Telescope, named after the recognized NASA executive James E. Webb, stands as a marvel in modern galactic investigation. This telescope represents a huge mechanical leap forward from its predecessor, the Hubble Space Telescope. A result of a cooperative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST surpasses the capabilities of its herald. It utilizes cutting-edge technology and a design enhanced for studying the universe in remarkable detail. Unlike the Hubble, the JWST delivers clear and sharp images of far-off celestial bodies. Working primarily in the infrared spectrum, this unique feature allows it to penetrate cosmic dust and capture celestial objects that were previously hidden from view. With its massive 6.5-meter primary mirror, composed of 18 hexagonal segments, the JWST surpasses the Hubble's reflector size. Positioned approximately 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits the Sun in sync with Earth, ensuring a stable and continuous view of the universe. Exploring the distant corners of the cosmos involves not just vast distances but also a kind of time travel. The JWST uses infrared instruments to observe celestial objects and events from billions of years ago. The light emitted by these objects, due to the universe's expansion, undergoes redshift, shifting from the visible spectrum to the infrared. Fortunately, the JWST can detect this infrared light emitted by distant celestial bodies, allowing scientists to study the birth of stars, investigate galaxy formation, and examine exoplanet atmospheres. Its latest groundbreaking discovery involves identifying an incomprehensible mass of galaxies at the edge of the observable universe. This finding casts doubt on the validity of our current cosmological models, prompting a reassessment of fundamental assumptions about how the universe came to be. To better understand how we arrived at this point, we should take a short journey through the history of space exploration. Early civilizations, such as the Greeks and Chinese, laid the foundation for understanding planetary motion by observing celestial bodies. In the 17th century, Newton's laws provided a theoretical framework for space travel. In the early 20th century, astronomer Edwin Hubble made groundbreaking discoveries in cosmology and observational astronomy. His observations revealed that distant nebulae were actually separate galaxies far beyond the Milky Way, reshaping our understanding of the universe's vastness. Hubble's law demonstrated that galaxies farther away were moving at greater speeds, providing evidence for the expansion of the universe. After World War II, the history of space exploration marked the beginning of the space race. The Soviet Union launched Sputnik in 1957, the first artificial satellite in orbit. Yuri Gagarin's historic orbital trip in 1961 and the Apollo 11 moon landing in 1969 were major milestones. Fast forward to 1990, when the Hubble Space Telescope was launched. It provided unprecedented clarity and stunning insights into the universe. The journey from ancient astronomical observations to the technological marvel of the James Webb Space Telescope highlights the continuous evolution of our understanding of the cosmos. Hubble Space Telescope, HST, revolutionized astronomy by capturing iconic images like the Pillars of Creation in the Eagle Nebula, revealing massive star-forming regions. Another remarkable achievement was the Hubble Deep Field, which captured thousands of galaxies in what seemed like an empty patch of space. Hubble also analyzed exoplanet atmospheres, detecting elements like water and organic molecules in distant worlds, hinting at potential habitable zones beyond our solar system. By studying the closest observed supernova, SN 1987A, it shed light on the life cycle of massive stars. These accomplishments solidified Hubble's legacy as a cornerstone of modern cosmology. The James Webb Space Telescope was designed to build on these technological advancements and deepen our understanding of the universe's origins. According to the prevailing Big Bang theory, around 13.8 billion years ago, the universe began as an incredibly hot and dense singularity. It rapidly expanded, giving rise to matter, energy, and the fundamental forces we observe today. As the universe expanded, it cooled, leading to the formation of atoms, stars, galaxies, and other cosmic structures. The Big Bang theory explains key phenomena, such as cosmic microwave background radiation, light element abundances, and the large-scale structure of the cosmos. Despite being widely accepted, the Big Bang theory faced skepticism in its early days. Alternative models, like the steady-state theory, proposed a universe with no distinct beginning. Concerns were raised about the lack of direct evidence for an initial singularity. However, most objections were addressed over time, with a major breakthrough occurring in 1965 when scientists detected cosmic microwave background radiation, strongly supporting Big Bang predictions. Missions like COBE and WMAP, along with advancements in observational technology, further validated the theory. Accurate measurements of cosmic microwave background radiation aligned remarkably well with theoretical forecasts. Enter the James Webb Space Telescope. Equipped with advanced infrared instruments, it can peer through cosmic dust and capture the universe's earliest light. Since it operates primarily in the infrared range, it can observe celestial objects formed shortly after the Big Bang. Its infrared capabilities allow it to study star-forming regions, celestial nurseries, and other cosmic phenomena invisible to the human eye. Infrared light has longer wavelengths than visible light, allowing it to penetrate interstellar dust, something the Hubble Space Telescope struggled with. The JWST can also observe cooler objects, such as exoplanets, brown dwarfs, and distant galaxies, which primarily emit infrared radiation. As celestial bodies move away due to cosmic expansion, their emitted light shifts toward longer wavelengths, a phenomenon known as redshift. The JWST's infrared instruments detect these redshifted signals, capturing light from the early universe and offering insights into its formation and evolution. Additionally, the JWST can observe energetic events, such as black hole mergers and newborn stars, which predominantly emit infrared radiation. This expands its ability to investigate hidden or previously inaccessible cosmic phenomena. The significance of JWST's discoveries. The James Webb Space Telescope's recent discoveries have introduced new challenges to our current cosmological models. The presence of massive, mature galaxies at such an early stage of the universe's history suggests that galaxy formation may have been much more rapid and complex than previously thought. One possibility is that the early universe had conditions that allowed galaxies to form at an accelerated rate, possibly due to higher densities of dark matter or different mechanisms of star formation. Alternatively, these findings may suggest gaps in our understanding of dark energy and its role in cosmic evolution. Scientists are now reconsidering key aspects of galaxy formation, such as the role of supermassive black holes. Observations suggest that some of these young galaxies already house black holes with masses equivalent to millions or even billions of suns. The question remains, how did these black holes grow so quickly in the early universe? Did they form directly from the collapse of massive gas clouds, or did they grow through rapid mergers and accretion? Implications for the Big Bang model. The presence of these ancient galaxies forces scientists to refine or even rethink certain elements of the Big Bang model. While the fundamental premise of cosmic inflation and expansion remains robust, new data from JWST suggests that the early universe may have evolved differently than expected. For instance, if galaxies formed and matured faster than our models predict, it could indicate that the standard timeline of structure formation needs adjustment. This could have significant implications for our understanding of dark matter, dark energy, and the fundamental physics governing the cosmos. Some researchers are even exploring alternative theories to explain these findings, such as modifications to the lambda cold dark matter (CDM) model, or considering the possibility that unknown physical processes were at play during the first few 100 million years after the Big Bang. The future of cosmic exploration. The discoveries made by JWST are just the beginning of a new era in astrophysics. As the telescope continues to gather data, scientists will refine their theories and develop new models to explain the mysteries of the universe's infancy. Future observations will focus on detailed spectral analysis of early galaxies, studying their composition, star formation rates, and the presence of heavy elements. Investigating exoplanet atmospheres, searching for signs of habitability, including water vapor, carbon dioxide, and even potential biosignatures. Exploring the nature of dark matter and dark energy, analyzing how these mysterious forces shape the large-scale structure of the universe. Mapping the first stars and black holes, understanding their formation and influence on early galaxy evolution. In the coming years, JWST will work alongside other next-generation observatories, such as the Nancy Grace Roman Space Telescope and the Extremely Large Telescope, ELT, to further expand our cosmic knowledge. A new chapter in our understanding of the universe. The James Webb Space Telescope has already begun rewriting the story of cosmic evolution. Each new image and data set it provides brings us closer to understanding the origins of the universe, the formation of galaxies, and even the potential for life beyond Earth. As we continue to explore the cosmos, we may find answers to some of the most profound questions in science. How did the first galaxies form? What is the true nature of dark matter and dark energy? And ultimately, what is our place in this vast, ever-expanding universe? One thing is certain, the discoveries made by JWST mark the beginning of a new era in astronomy, one that promises to challenge, refine, and expand our understanding of the cosmos for generations to come. The fundamental nature of the universe includes its composition, structure, and the forces governing its evolution. While the Hubble Space Telescope was revolutionary for its time, it had limitations in observing the early universe. Its main limitation was its inability to effectively penetrate cosmic dust and detect the infrared light emitted by ancient galaxies. Older telescopes relied on visible and ultraviolet light observations, making it challenging to explore the early universe, as these wavelengths were absorbed or distorted by interstellar dust and gas. The James Webb Space Telescope, JWST, represents a significant leap forward in studying galaxies from the universe's early stages. Unlike its predecessors, the JWST can observe celestial objects that formed within a few 100 million years after the Big Bang, using its infrared sensitivity and modern imaging techniques. Its capabilities have uncovered an abundance of ancient galaxies, offering remarkable clarity and detail in understanding the universe's evolutionary history. Preliminary results from JWST observations have stirred debates in established cosmological models. The detailed data challenges several aspects of current theories, causing cosmologists to reconsider fundamental principles governing cosmic evolution and structure. Discrepancies between observed data and theoretical forecasts have sparked intense discussions within the scientific community. JWST observations have revealed a larger number of galaxies in the early universe than anticipated by existing models, suggesting a more complex and rapid evolution process. Some early galaxies appear more developed than expected, challenging conventional models that predict slower development. The discovery of an immense number of galaxies questions the assumed distribution and arrangement of large structures, revealing a more intricate and denser cosmic web than previously thought. These observations raise fascinating questions and avenues for further exploration. The existence of large structures challenges early models of cosmic structure formation, prompting researchers to refine their models for a better explanation. Understanding how such vast structures gathered rapidly after the Big Bang presents a puzzle that requires an explanation that does not violate fundamental principles of cosmology. Significant disparities between the conditions of the early universe and predictions based on existing models have also been revealed. These differences could suggest previously unknown processes, unanticipated circumstances, or unidentified cosmic phenomena. In simple terms, scientists are rethinking and improving our models of the universe in response to these changes. Currently, all we can say is that further exploration is required to incorporate these surprising observations into a more comprehensive understanding of the universe. Initial observations frequently offer exciting glimpses into the universe, but in-depth investigations sometimes reveal differences. For example, early observations may show specific properties or arrangements within distant galaxies that, upon closer examination, reveal fluctuations in their composition, structure, or evolutionary pathways. In conclusion, enormous cosmic phenomena are incredibly complex and require careful investigation to accurately understand their true nature. Spectroscopy, a method that helps unravel the properties and history of celestial objects, is an essential tool in this effort. It involves analyzing the light emitted or absorbed by astronomical objects. By examining the properties of this light, spectroscopy provides detailed information about the chemical composition, temperature, density, and movement of celestial bodies. This analysis helps us understand the origins, development, and contributions of celestial bodies to the cosmic tapestry. The JWST has uncovered numerous cases where initial observations differed from later investigations. For instance, initial observations of distant galaxies suggested a simple structure primarily dominated by lighter elements like hydrogen and helium, aligning with theoretical expectations. However, spectroscopic analysis using the JWST revealed fascinating variations, identifying signatures of heavier elements or compounds that were previously misidentified or misunderstood. This challenges conventional ideas about the early universe's chemical composition and the mechanisms responsible for their development and distribution over vast distances. Initial assumptions about galaxies in the early universe were founded on preliminary observations suggesting a relatively uniform pattern of development and organization. However, more in-depth examinations by the JWST have revealed a much more diverse and complex array of chemical compositions within these galaxies. The James Webb Space Telescope continues to redefine our understanding of the cosmos by shedding light on previously hidden corners of the universe. One of its most exciting capabilities is its ability to study exoplanets in unprecedented detail. By analyzing the atmospheres of planets orbiting distant stars, the JWST can detect crucial chemical signatures such as the presence of water vapor, carbon dioxide, and organic compounds like methane. These findings provide valuable insights into the potential habitability of exoplanets and the conditions that might support life beyond Earth. In addition to exploring distant worlds, the JWST is transforming our understanding of star formation. It can observe the birth of stars in regions where young stars are surrounded by dense clouds of gas and dust, which optical telescopes cannot penetrate. With its ability to detect infrared light, the JWST captures the faintest glimmers of these new stars as they emerge from the darkness, offering a clearer picture of the processes that lead to star and planetary system formation. By studying these regions, astronomers are gaining a deeper understanding of how stars like our Sun come into existence and evolve over time. Another remarkable aspect of JWST research is its ability to peer into the hearts of galaxies. Black holes, particularly supermassive ones, are believed to reside at the centers of most large galaxies. The JWST's advanced instruments allow scientists to observe the behavior of matter around these black holes, providing new insights into their growth, their influence on galactic evolution, and the powerful jets of energy they produce. These findings help astronomers piece together the story of how galaxies and their central black holes evolve together, influencing each other's growth. Unveiling the mysteries of dark matter and dark energy. One of the most intriguing areas of research that the James Webb Space Telescope, JWST, contributes to is the study of dark matter and dark energy, two enigmatic components that together make up about 95% of the universe. While dark matter is thought to provide the gravitational framework for galaxy formation, dark energy is believed to drive the accelerated expansion of the universe. JWST's advanced observational capabilities allow scientists to study how galaxies are distributed across vast cosmic distances, helping to infer the presence and influence of dark matter. By analyzing gravitational lensing, where the gravity of massive objects bends light from more distant galaxies, researchers can map the unseen distribution of dark matter with unprecedented accuracy. These findings may refine our understanding of how galaxies cluster and evolve under its influence. Similarly, JWST is contributing to the study of dark energy by measuring the redshifts of distant supernovae in galaxies. By examining how light stretches over time as the universe expands, astronomers can refine models of cosmic acceleration. Any unexpected variations in these measurements might challenge our current understanding of dark energy, potentially leading to groundbreaking revisions in fundamental physics. The search for the first stars, population 3 stars. JWST is also on a quest to detect the universe's first stars, known as population 3 stars. These ancient stars, formed just a few 100 million years after the Big Bang, were composed almost entirely of hydrogen and helium, as heavier elements had not yet been forged in stellar cores. Until now, no direct observations of population 3 stars have been confirmed. However, JWST's infrared capabilities allow it to probe deeper than ever before, potentially capturing the faint signatures of these primordial stars. Detecting them would be a monumental breakthrough, offering insight into the earliest stages of star formation and the chemical evolution of the cosmos. Revisiting the origins of supermassive black holes. One of the biggest mysteries in astrophysics is how supermassive black holes, which are millions to billions of times the mass of our Sun, formed so early in the universe. Traditional models suggest that black holes grow from the collapse of massive stars and gradually accumulate matter over billions of years. However, JWST has detected supermassive black holes in galaxies that existed less than a billion years after the Big Bang, far earlier than expected. These findings raise the possibility that alternative mechanisms, such as the direct collapse of massive gas clouds into black holes, might have played a role in their rapid formation. The implications of this discovery could reshape our understanding of black hole growth, galaxy formation, and the role of black holes in shaping the cosmos. The future of JWST discoveries. As JWST continues its mission, each new observation refines our understanding of the universe. The telescope is expected to operate for at least a decade, during which it will expand our knowledge of exoplanets, dark matter, dark energy, and the fundamental forces shaping the cosmos. Scientists eagerly anticipate future collaborations between JWST and other next-generation observatories, such as the Nancy Grace Roman Space Telescope and the Extremely Large Telescope, ELT. Together, these instruments will provide complementary data, helping astronomers piece together a more complete picture of our universe's history and evolution. A new era of cosmology. The discoveries made by JWST highlight the ever-evolving nature of scientific inquiry. Every new revelation challenges existing paradigms, leading to deeper questions about the origins, composition, and fate of the cosmos. While many mysteries remain unsolved, one thing is certain: the James Webb Space Telescope is redefining our understanding of the universe and paving the way for future generations of cosmic explorers.